Welcome back to MCB 170, Society and the Brain. This is Lecture 2, pre-recorded Lecture 2, which covers Part 2 of Module 1. The topic of Module 1 is Wired for Society. We're talking about how the brain is wired for society, how there are specific brain regions that are specialized not only for communication between human beings, but also for certain aspects of social interaction. And we left off last time talking about the four lobes of the cerebrum, shown here as different colored regions of the cerebral cortex, which is the outside of the cerebrum. They are the frontal lobe, the occipital lobe, the temporal lobe, and the parietal lobe. You'll remember that from last time. This slide again shows those same lobes. Now the brain is flipped over, so this is the front and that's the back: frontal lobe, occipital lobe, parietal lobe, and temporal lobe. And this diagram has two really important aspects to it. It shows us two important things about the cerebrum. I want to point out a central feature here called the central sulcus. Remember, a sulcus is a valley, a gyrus is a hill in the folded up structure of the cortex. This is a very important sulcus, the central sulcus. It divides the frontal from the parietal lobe, and it also divides the sensory part of the brain from the motor or action part of the brain. So it turns out that the lobes in the back, parietal, occipital, and temporal, are involved mostly with sensation and perception, whereas the front of the brain is involved with motion, action, and planning. So the red parts are for motion, action, and planning. The blue parts are for sensation and perception. This slide illustrates that very nicely in this color code. Also, you notice that there are different shadings of blue and red. So the dark shades are what are known as primary cortex. Primary as in elemental. So the very back of the brain, the very back of the occipital cortex is the primary visual cortex. It's involved in sensing the simplest visual features, which are basically spots of light. The primary somatosensory cortex here, this part of the parietal lobe, is involved with sensing the simplest sensory, the touch perceptions. Primary auditory cortex is involved with sensing the simplest auditory inputs. As you move away from the primary regions in the brain, the sensory processing becomes more and more sophisticated. Higher and higher levels, higher and higher features are extracted from the sensory input. This part of the parietal lobe is called association cortex, because what's happening here is input from the different sensations is coming together to sense more and more sophisticated collections, really, of sensory attributes. Similarly, in the frontal lobe, the primary motor cortex is involved in making the simplest movements, like moving my index finger like that. Would be happening in a part of the primary motor cortex right about there, say. As you move away from primary motor cortex, now you're encoding more and more sophisticated movements, like movements of the mouth, for example, in speech, which we'll talk about in a little while. Up here, you're talking about planning, more and more sophisticated kinds of plans, future actions. In fact, the very front of the frontal lobe, we still don't even know what it does. We'll be talking about prefrontal cortex, which is about here, which is known as the seat of reason. It's where we do most of our thinking, a lot of our cognition, and especially a lot of our social cognition. The prefrontal cortex is going to be a very, very important area, maybe the most important area that we'll be discussing in the course. And I'll show you a slide that shows the prefrontal cortex in detail in a little while. So the two most important things about this slide, what it shows us is the back of the brain, parietal, occipital, temporal. That's involved in sensation and perception. The frontal lobe is involved in action and motion. Also, you have primary cortices and secondary and higher order cortices, where the simplest things happen in the primary cortex and more sophisticated things happen as we move away anatomically from the primary cortices. And so now let's talk about parts of the brain that are specialized for communication. What I'm going to show you is that parts of the brain that are involved in communication occupy relatively large pieces of very, very high order cortex. Okay, so here's another view of the brain, the front of the brain, the back, frontal lobe, parietal lobe, occipital lobe, temporal lobe. Here's our central sulcus. This is the movement and action part of the brain. This is the sensation and perception part of the brain. I draw your attention to these two regions, the blue region, Wernicke's area, and this orange region, Broca's area. Wernicke's area is involved with understanding language. Wernicke's area is involved with understanding language, whether it is written or spoken. Without Wernicke's area, you could not understand language. Broca's area is involved with producing language, both spoken and written. When you produce intelligible language, whether you're speaking it or writing it down, you're using Broca's area. What about individuals who are blind or can't speak? They use Wernicke's area and Broca's area also to understand language, either through Braille or sign language. Notice, these two areas are critical for communication, for understanding communication and for producing communication, verbal communication. And they're occupying very, very large areas of very high order cortex. They are important areas for communication. Obviously, our human brains wouldn't devote such large areas of high order cortex to communication if we didn't need to communicate. We do need to communicate with each other, and Wernicke's area and Broca's area illustrate, I think, very strongly how our brains are wired for society. Let's consider another form of communication. Here's an interesting fact. Humans can have up to 43 facial muscles. Some humans only have 42 or 41 facial muscles, which is very interesting. But we can have up to 43 different facial muscles. That's more than any other animal known to exist. The simplest animals have very few facial muscles, like fish and frogs. I mean, fish, I don't think, have any facial muscles. They just have the same expression all the time, no matter what they're doing. But humans have lots and lots and lots of facial muscles. And what do we use those for? For making facial expressions. And these are considered to be the 6 essential facial expressions: disgust, fear, joy, surprise, sadness, anger. But of course, we can express combinations of these features, of these emotions in our facial expressions. They can be very, very sophisticated. So we have lots and lots of muscles to produce facial expressions, and we communicate through these facial expressions. We can show how we feel, and we can see how other people feel. So we have very high order levels of our brain that control our facial muscles and that also can perceive facial expressions. Shown here is what is called the face responsive region in the anterior temporal lobe of humans, otherwise known as the fusiform face area. The fusiform face area, I'll show you a slide with that specifically in a few minutes. Again, this is very, very high order. This is almost at the very end of the temporal lobe. Very, very high order temporal lobe devoted to interpreting facial expressions. Again, the brain wouldn't devote such a large area of very high order cortex facial expressions if we didn't need to communicate with each other through facial expressions. But we do, and humans are extraordinarily good at it. In a minute, we'll talk about some more specific regions that mediate social interactions. But before we get there, I want to talk about the two main groupings of social cognitive processes. The processes of social cognition can be subdivided into those that are automatic and those that are controlled. Automatic and controlled. We're talking about automatic and controlled processes all the time. This is a central concept for this course, that the processes of social cognition can be essentially divided into automatic and controlled processes. Automatic processes are fast, spontaneous, reflexive, shared in common with a wide range of species, not just humans, but also other animals, and they're dominant in early development, and they often involve emotions. So when you think about automatic processes, you're thinking about relatively low-level neural functions involving emotions, involving innate urges, involving instincts. We're largely born with them. We can influence them, we can modulate them, but they come kind of pre-wired in us. On the other hand, controlled processes are slow, effortful. They require effort and reflection. They arise late in evolution and development. So we have the best controlled processes as human beings, and we don't have good controlled processes when we are young. We have to develop them, and we'll talk about the development of controlled processes later in the course. Controlled processes often involve language-based declarative reasoning and reflective thinking. Okay, we'll talk about declarative reasoning and reflective thinking a lot later on in the course, but it involves language, it involves thinking through a problem. So in a controlled process, you're thinking through a situation. What is morally appropriate? What ethically should you do? And then you can apply that thinking to control your automatic processes and also to control your deliberative behavior. Okay, interaction between automatic and controlled processes is critical for all of the social cognition we're going to be discussing in this course. I can't emphasize that strongly enough. Okay, so here are some specific regions of the brain that mediate not just communication, but social interaction. These are some of the main parts of the brain that are involved in that provide you with social intelligence. These are the parts of the brain that provide you with social intelligence. And I just want to show you where they're located in the brain, just to give you an idea of that. You don't really have to remember specifically, which sulcus and which gyrus is which on the brain, because this isn't really a neuroanatomy course. I just want to show you where they're located. And in the next slide, we're going to talk about what they do, and that's what you need to remember. Okay, so here's a view of the brain, the cerebrum, cerebral cortex. This is the front, this is the back, frontal lobe, occipital lobe, parietal lobe, temporal lobe. This area right here is the prefrontal cortex. Very important area, very important area. It's the seat of reason. It helps us think through our social interactions. It's really the prefrontal cortex that enables us to behave appropriately, to treat others the way we really want to treat them, according to our morals and values we've internalized from society, okay? It's really the prefrontal cortex that lets us do that. As we talked about in part one, the development of our brain, the development of our personality, the development of our psyche has a lot to do with our social interactions. It wouldn't develop normally without them, but we do have some control over it. We have some choice over what morals and values we choose to internalize and to make our own. When we do that, we're using our prefrontal cortex. When we choose what from society, what from culture we're going to internalize as our own morals and values, and when we use them to control our behavior, to control our deliberate behavior and to try to modulate our automatic responses, we're using our prefrontal cortex. That's why the prefrontal cortex is really the star of the show for this course. The other structure shown in this particular panel is the superior temporal gyrus. The superior temporal gyrus is right there. It's in the temporal lobe, and it's toward the top of the superior lobe, and it's a gyrus, so it's like a hill, superior temporal gyrus. On this panel, we also see the superior temporal gyrus. Shown also, shaded in gray, is the somatosensory cortex, primary and secondary somatosensory cortex. Those are really just landmarks, because what this panel really wants to show us is a structure called the temporoparietal junction. It's right there, it's uncolored. The temporoparietal junction. Here's a temporoparietal junction right here, right above the superior temporal gyrus, temporoparietal junction. That's an important one for social cognition, and we'll talk about what it actually does in the next slide. This is an interesting image. It's really an image of a brain with a big chunk of the cortex taken away to reveal another chunk of the cortex. Remember, the cortex is just folded on itself like crazy. And there's one very, very big fold. And the cortex on the inside of that very, very big fold is called the insula. It's kind of inside the fold, so it's called the insula. We'll be talking about the insula a lot, and in the next slide, I'll tell you exactly what it does. This is an image of the cerebrum looking from below. Okay, so this is like where your Adam's apple is, right? The top of your head is on the other side of the screen. And what we're seeing here is the fusiform gyrus. This is the same as that part of the here's the fusiform gyrus here. This is the face area. The face responsive region in the anterior temporal lobe, also known as the fusiform gyrus. That's this part of the brain right here, critical for interpreting facial expressions. This is another part of the frontal cortex, called the medial orbitofrontal cortex, orbitofrontal cortex. Why is it called orbitofrontal? Well, the orbit where your eye is, it would be right about here. So it's right above, this part of the cortex is right above your eyes, medial orbitofrontal cortex. The orbitofrontal cortex works with the prefrontal cortex in helping us behave appropriately. Both are kind of involved in reason and in emotion, controlling emotions and interpreting emotions. But the prefrontal cortex is more associated with reason, while the orbital frontal cortex is more associated with emotion. But they do similar things. They do similar things and they often work together. They're very, very important regions of our brain. This image of the cerebrum is split in half. So it's as though you took this image and cut it on a front back line. This is looking at the inside surface of the cerebrum. So you can see the thalamus would be here. This is called the corpus callosum, which is a bunch of axons that connect the two hemispheres, left and right. So this is split left and right. So we're looking at the inside of the cerebrum. Here again is the orbital frontal cortex, as shown here. And this region is the anterior cingulate cortex. So the cingulate cortex is this part of the cortex on the inner surface of the cerebrum. And anterior means front, posterior means back. So the anterior cingulate cortex is the front part of the cingulate cortex, where the cingulate cortex is the part of the cortex between the hemispheres. Anterior cingulate cortex, very important structure. We'll talk about what it does in the next slide. And finally, on this slide, I want to point out the amygdala. The amygdala is a critical structure. It's the king of the automatic processes. It's connected to neocortex, but it really isn't a cortical structure by itself. It's more primitive than a cortical structure. But it's down here at the base of the brain, and it communicates extensively with the rest of the brain, the amygdala. Again, this is a paper by Ralph Adolphs, The Social Brain, Neural Bases of Social Knowledge. Excellent article in the Annual Review of Neuroscience. If you're interested in this topic in detail, you can download this article for free, either on PubMed or Google Scholar or some other search engine. However you can dig it up. If you can dig it up, the university will give you access to that article for free. Okay, so here's what these places do from Adolphs. And this is very important. I want you to read this very, very, very carefully and make sure that you know the information on this slide. This will be very important for the quiz for Module 1. Let's talk about the amygdala. When I say amygdala, you're going to think fear. Amygdala, often associated with emotional processing. Like I said, it's the king of the automatic processes. Associated with emotional processing, especially fear, provides a rapid automatic influence on social cognition. It's an automatic process. Rapid automatic influence. Here's prefrontal cortex. Technically, it's known as the ventromedial prefrontal cortex. Sometimes I'll call it ventromedial prefrontal cortex. Often I'll leave off the ventromedial and just call it prefrontal cortex. Anyway, ventromedial prefrontal cortex is important for making decisions. It's associated with reason, thinking and reason. The ventromedial prefrontal cortex is needed for reading social cues and acting appropriately. Acting according to your morals and values. It's being how you know you're supposed to be. When you're being how to be, you're using your prefrontal cortex. If you have damage to your prefrontal cortex, it impairs your ability to act appropriately in social situations. The temporoparietal junction, involved in visual processing from different perspectives, and it gets its input from the superior temporal gyrus. So I showed you where the superior temporal gyrus was in relation to the temporoparietal junction. Okay, so the temporoparietal junction gets visual information from superior temporal gyrus. It's involved in visual processing from different perspectives and in reasoning about the intentions and beliefs of others, along with prefrontal cortex. So temporal-parietal junction is necessary for reasoning about the intentions and beliefs of others, and it works with in that with the prefrontal cortex. Obviously very important for social interactions and for social cognition. The insula. The insula is another important region for automatic processes. The insula is associated with stimuli concerning other people, especially with negative feelings such as disgust or pain. So when I say insula, you should think disgust. And we'll see many examples of that as we go along in the course. So amygdala is automatic, associated with fear. Insula is automatic, associated with disgust or pain. Okay. Prefrontal cortex, associated with reason and interpretation of emotions. And it works with orbital frontal cortex. Temporal parietal junction, reasoning about the intentions and beliefs of others, also works along with prefrontal cortex. Ventral medial prefrontal cortex, orbital frontal cortex, temporal parietal junction, those are controlled processes. These two are controlled. Amygdala and insula would be automatic. How about the anterior cingulate cortex, which is between the hemispheres? It monitors conflict. So when you hear anterior cingulate cortex, you should think conflict. Very interesting area. It's going to monitor conflict between the automatic processes and the controlled processes. The anterior cingulate cortex monitors conflict and integrates this with emotion to motivate behavior. The anterior cingulate cortex is thought to play a role in updating social information concerning other people. So when your feelings and your thoughts about a person are in conflict, you can activate the anterior cingulate cortex and it'll help you figure it out. Okay. Very interestingly, we have amygdala and insula, automatic processes. Prefrontal cortex and temporal parietal junction and orbital frontal cortex, controlled processes. The anterior cingulate kind of mediates between the two. When it detects a conflict between controlled and automatic processes or other kinds of conflicts occurring in your brain, it can activate the prefrontal cortex to help resolve the conflict. Those are very, very important interactions that will be at the heart of many of the processes that we discuss in this course. Once again, this is a very, very important slide. This information is very important. I want you to know it, and you'll see how important it is when you take your quiz for Module 1 this week. And here's an example of how important the prefrontal cortex is. This is the famous example of Phineas Gage. Many of you probably already know this example. Phineas Gage had a metal rod driven through his skull as a result of a workplace accident. What specifically was he doing? He was working on the railroad, and they needed to blow up a bunch of rocks to get him out of the way. So he was tamping down some explosives with a tamping rod, this iron tamping rod, and the explosives went off, and it drove the rod up through his cheek here, through his orbit, where his eye is. Here's the orbit. It drew it up through his eye, through the orbital frontal cortex, through the prefrontal cortex, and the rod came flying out the top of his head. So it basically destroyed his orbital frontal cortex and his prefrontal cortex, and a lot of the rest of his frontal cortex along with it. As a result of that, he could no longer behave appropriately. This trauma destroyed portions of his ventromedial prefrontal cortex. His personality changed from reliable and respectable to unreliable, disrespectful, and profane. Very interesting article on this by Antonio Damasio in Science, again, available to you for free through the university. So that's the famous story of Phineas Gage, and many of you have already heard that story. Now you know why he couldn't behave appropriately, because the rod wiped out his prefrontal cortex and other important parts of frontal cortex. This is a beautiful example from this paper on conflict resolution. Very interesting experiment with a very clever design. These researchers realized that faces are recognized near the highest levels of visual processing in the fusiform gyrus, which we talked about, and conflicts are detected in the anterior cingulate cortex, where attentional control is then brought to bear by the prefrontal cortex. Now let's talk about this example. What did they do? They generated a conflict by showing subjects a picture of an actor with the name of a politician. Well, they show them a picture and a name. And in non-conflict cases, the name matched the picture. But in conflict scenarios, the name was different from the picture. The name here is Mao Zedong, and the picture is one of Robert De Niro, the actor, Mao Zedong, the politician. Conflict. The face of the actor, Robert De Niro, activated the fusiform face area. The name activated the word area in probably Wernicke's area. There was a conflict between these two. That conflict was detected by the anterior cingulate cortex, which engaged the prefrontal cortex to help the subject resolve the problem. The resolution in this case was just realizing that there was a conflict, realizing that the subject had been tricked, that the name really did not correspond to the photograph. This is a kind of a fun, almost kind of a whimsical example where the kinds of conflicts we'll be talking about mostly in this course will be moral and ethical conflicts, where you're afraid of someone you shouldn't be afraid of, or you're disgusted by someone you shouldn't be disgusted by. And your moral values and ethical principles tell you, yeah, you really shouldn't be reacting that way. When that happens, your anterior cingulate cortex has detected the conflict. It then recruits the prefrontal cortex mainly, but it also could recruit orbital frontal cortex and other parts of your frontal cortex to resolve the problem, to sort things out, and even to change how you respond in that situation in the future. And let me say, especially to change how you respond to that situation in the future. In other words, how you grow as a person. Okay. So in this course, we'll be talking a lot about the neurobiological level of your growth as a human being as you become a more moral and ethical person, as we all do. It's very important to point out that automatic and controlled processes work together. Reason and emotion work together. Pretty much everything we do involves a combination of reason and emotion. You know, there's no such thing as a human being who's like, Dr. Spock, or Mr. Spock on Star Trek, who is pure logic. None of us are pure logic. Everything we do is a mixture of reason and emotion. Antonio Damasio describes a patient who had a lesion, actually damage to parts of his brain, and he didn't have emotions anymore. He lost his emotions. And you would think that a person who lost their emotions would be extremely logical and would be very good at problems in logic and philosophy and math, right? But when Antonio Damasio asked this person to do a math problem, he didn't want to do it. He had no motivation to do it because motivation is an emotion. He said, forget about it. I'm not going to do that problem. I'd rather just sit around and eat pretzels and watch football games. So pretty much everything we do, even things like mathematics that you think wouldn't involve emotion, well, it involves a lot of emotion because it involves motivation. You have to be emotionally motivated to do hard mathematics problems. But even moral judgments that you think would be purely logic are not purely logic. They rely on a mixture of automatic and controlled processes, which include emotion and intuition, but also explicit concepts of reciprocity, fairness, loyalty, and respect. Okay? So, emotion and intuition, automatic processes, they happen fast, we're not aware of them, but also explicit concepts, which involve reason, such as reciprocity, egalitarianism, fairness, loyalty. We can explain these, they're declarative, we can declare them. They involve declarative reasoning, they involve logic. And the prefrontal cortex and the anterior cingulate cortex often work together in mediating social cognition. And this is very important. For example, the two are active when an emotionally potent moral judgment must be overridden to arrive at a decision that benefits the group. In other words, if you have a reaction, a moral reaction, a kind of an innate urge that is not going to help you or your group, anterior cingulate cortex will recruit prefrontal cortex to help you resolve that conflict. And we'll talk about this more and more as we go along in the course. The important point here is that moral judgments rely on a mixture of automatic and controlled processes. They work together. In almost everything we do, they're not separate. And they work in both directions. Automatic and controlled processes work in both directions. For example, controlled processing allows us to alter our emotional responses but emotions can also influence our deliberative choices. They work in both directions. You might have an initial emotional reaction to a particular situation, but your controlled processes will be engaged to help you behave appropriately even in those circumstances. On the other hand, the way we feel about things can influence our reason. you might feel that you shouldn't trust a particular person in a particular situation, and maybe that intuition is right. So our intuition affects our reason, and our reason can affect our intuition, and they're always operating together, even in cases where you think they wouldn't. So this is the picture that emerges, and this diagram is central to our course and central to the society and brain approach that we're taking. This box is the individual brain, composed of controlled processes and automatic processes, and there's a two-way interaction between them. Automatic processes, emotion, intuition. Controlled processes, reason and learning. But our control processes are influenced by culture. The morals and values that we download from culture, we then use to control our automatic processes and our deliberative behavior. This idea, as expressed in this diagram, is central to what we'll be talking about throughout our course in society and the brain. And the interesting thing is that brains together, interacting together, produce culture, but then culture turns around and influences individual brains. So we by communicating and using our processes of reason and social interaction essentially create culture. And then culture turns around and influences us. We internalize cultural values, moral values, and moral principles into our control processes and use those to control our behavior and to modulate our emotions. And culture is developing. As we move through the centuries, human culture is developing. And I think it's very true that we're getting better as a species. Our culture is developing and we're improving and we're making human life better and better for everyone as we move through the centuries. And this is illustrated in a book written by Steven Pinker. I think this is one of the most important books out there. It's called The Better Angels of Our Nature, where he documents how violence has declined over the centuries. Violence and murder have declined. People don't kill each other as much as they used to. They're not violent toward each other as much as they used to. They're even kinder on a social level, even verbally. There's more compassion, there's more tolerance, there's more understanding. And you see this developing even now, right? We're continuing to try to promote better understanding between people who are different, for example. In Pinker's book, he has chronicled how, for example, the homicide rate in America has been decreasing since recorded time, since Europeans arrived in America back in the 1600s. The murder rate has declined, and violence of all kinds has also declined. This is true in the United States. It's also true in many European countries. Violence is continuing to go down. The homicide per 100,000 people in like Scandinavia is, one or less than one. The murder rate is very, very low. The rate of violent attack is very low. So violence and murder are going down. Why? Why is that? Well, Steven Pinker attributes it mostly to civil society, to governments and laws and police who enforce the laws. We'll talk about that more as we go along in the course. But I think a big factor has to do with culture, because just as the homicide rate has declined in America and Europe, well, the literacy rate around the world has increased over that same period. More and more people can read. And what do we read about? What do we read about? Well, let's look at the 100 most influential books ever written. Here's the first 20 in this list of most influential books. I'll let you go over this at your leisure, but you'll see when you go through this that the majority of these influential books are books about religion or philosophy. Religion or philosophy. Religion and philosophy are about morals and ethics, about how we should be, how we should behave, and why. I think that throughout history, our moral development and ethical development through religion, through philosophy, through learning, has improved culture Those cultural values have been internalized by us into our control processes, and we've used those to influence, to guide our deliberative behavior, and to modulate our emotions in a way that benefits everyone. And this is a theme that will recur over and over in the course. We'll come back to this thought, and as expressed in this diagram, over and over again, that our social processes are divided into controlled and automatic. Automatic is emotion, controlled is reason. We use our reasons to control our automatic responses, our emotional responses. And by what do we control them? Well, we're not born with moral values and ethical principles. We have to download them from culture. The interesting thing again is that brains together, individual brains together, produce culture, and culture, a lot of culture involves moral values and ethical principles. We develop these together through culture, and then we internalize them from culture and get them into our own brains and use those values to control our emotional responses. And this is another way in which society is composed of brains, but then we in society, through our interactions, create norms, behavioral norms, ethical principles, moral values that we share. We internalize them back into our brains, and we use those values to control our behavior in pro-social ways. Okay, this concludes part 2 of Module 1 and also concludes Module 1.